No, you're good. I'm glad that you're reminding me. Hey, so guys, today, but what I've done is, and I'm becoming increasingly convinced that when I finally reach that summit of my craft, that I'm basically going to take AP chemistry and condense it into like 24 charts. Because increasingly, as I get better and better at teaching this, if you noticed, I like to share charts. Here's a chart. So I'm going to propose to you that the vast majority of the note-taking that you might consider doing today is unnecessary because of this. No, and you won't need to. Because, guys, to be honest with you, this chart is kind of like question number 4 out of the homework. It's way too many words. It's simpler, but it's not simple. But what you're going to find as you get into this material is the concepts, because of all the good work you guys have done up until now, understanding the things that you know about aqueous chemistry, guys, this is it's interesting. You'll find it interesting. So, with that said, there's one thing that we need to talk about that's sort of not random, but it doesn't fit into the big idea today, but it doesn't really fit anywhere, so let's just do it now. So this you do want to write down because it's not a part of what I just gave you. We need to talk about what are called polyprotic acids. And guys, I love that this year I can say this without alienating anybody. You're really going to understand polyprotic acids when we titrate them in third period. It's interesting. But this is the, you guys know this, right? This is the first year where I've had everybody A2 and A3. Did you guys not know that? Yeah, this is the first year that's been the case. So that's what's allowed us to switch second and third period, right? So every other year I've had to say, guys, polyprotic acids, let's talk about it a lot, knowing that those few kids that weren't in lab would never see this again. But I don't have to do that with you, but we will introduce it. So polyprotic acids, poly means many, protic is protons, which you know to be hydrogens, which makes a ton of sense because acids give away hydrogens, and now all this fits together. So a polyprotic acid is an acid that involves more than one, I'm fairly certain that's not a word, protonatable, giveawayable, goes awayable. But actually, guys, there is a, yeah, that's right. There is a word for it. We call these acidic hydrogens, which makes sense, right? It's the hydrogens that go away. And you may remember from when we were doing ice boxes last time, remember, I think it was even the formic acid one, where we had to ask ourselves which hydrogen goes away. And what did we learn? It's the ones on the end, bless you. It's the ones on the end, right? Could be the front or the back, but it's not the ones in the middle. So those are the hydrogens that we're talking about. But guys, it turns out that some molecules have more than one hydrogen that can go away. We call these the polyprotics. So you ready for a deep thought? How many of the strong acids are polyprotic? One. Which one? Sulfuric acid. Guys, that is the only acid that has more than one hydrogen. Therefore, there's only one polyprotic acid. Strong polyprotic acid. There's hundreds of weak polyprotic acids. So what do you need to know about them? Well, guys, to help you understand this, we're going to talk about not sulfuric acid, but sulfurous acid, which is not H2SO4, it's H2SO3. So guys, H2SO3 is not a strong acid. So what does it do? Well, it does this. Oh, yeah. So not this, but this is amphoteric.
Yeah.
Yes. It's frightening that I knew what you were talking about. I know. I'm slowly over time, I'm starting to think like you, Brandon. And I know. Did you see how I walked right up to that and then I turned and walked away? I was going to say something really snarky about us having really good mental health coverage with our, but I didn't. Except for I did. I know. So guys, you understand, right, that this is not a strong acid. And so consequently, what we do is we talk about its Ka value. And it's interesting and contextually frightening. Oh, yeah. Yeah, so what does 1 mean? And guys, this is actually a convention. I don't know the right word. This is a way of writing things that you need. What that means, right, it means the first proton. Ka1 for a polyprotic acid is the Ka value for the first proton going away. But then, guys, you'll notice, and I call that the conjugate base, and that makes sense? Yeah? The conjugate base still has a hydrogen, and it can release that second hydrogen. This represents that process. You can write down anything. It is stuff you need to know. Yeah, so this isn't covered in this. But if you want to just print the notes. So I know that you do. You'll learn to not like writing when you get to college because you just can't keep up. So, guys, guesses, thoughts, predictions. What will the Ka value be relative to Ka1? What will the Ka value be for the second protonation? It is less. Let's talk about why. Well, guys, and this isn't the complete answer, but I think it'll be satisfying. Notice the charge of this particle. It's negative. And because it's negative, it's harder for a positive proton to leave. We'll talk more about why it's harder next time. But for now, guys, understand it is harder. As a matter of fact, it's 1,000,000 times harder. I mean, thereabouts. But it's 6 orders of magnitude-ish harder for that second proton to leave. And guys, this is always the case. Can I use the word subsequent, following? Let me say it backwards or forwards. The first protonation is always the strongest, and it always gets weaker. This is what is called a biprotic acid. There are triprotic acids. There could be 4 protic acids. I don't know. I can't think of any. It could.
It would never get rid of all 4.
It would be really unlikely. So what do we do with this? Well, guys, general observations. And again, we'll come back to this in lab. But first of all, this is always true. The Ka for the first ionization is always the highest. And you don't need to write this down, but just to make sure we talk about it. For now, we're going to understand that being a function of the charge of the ion that's left after the first protonation. On Tuesday, we're going to talk more about what actually determines the value of Ka. You're going to find out that it's the polarity and the, what's the other word? Polarity and, no, it's strength, but there are other factors that lead to, we'll talk Tuesday. But guys, the other thing you need to understand is this, and I would strongly encourage you to paraphrase. When you're figuring out the pH of a polyprotic acid, if the second protonation is more than 1,000 times, let me say that differently. If the Ka for the protonation of the second proton is more than 1,000 times smaller, you can disregard it when figuring out pH. So, and I want to draw you, I want us together to draw a picture. Absolutely. You could disregard Ka2 anytime after 10 to the negative fifth. And just write down what you need to write down, and then we're going to draw a picture together. No, so the difference is 10 to the third. So if this is -2, that could go to -5. So guys, y'all caught up? So here's the question here's the task that I'd like to engage with you that's going to help you better understand this. We've got this, right? So if down below, I got rid of the additional notes. Draw yourself the beaker. And let's not include water. But here's what I want you to do. In a beaker of sulfurous acid, what's in the beaker? And don't draw the water. And guys, understand, you do not have the freedom right now to say, I'll wait to see what Knappenberger writes. Because this is what the AP test looks like in May. Tomorrow. It used to be that the AP test was all math. But guys, they have surrendered half of the math in exchange for let's draw pictures. So if you're sitting there right now going, I don't know what's in the beaker, so I'm not going to engage, I'm just going to copy later. Tomorrow's coming, and you're training yourself to be helpless. Don't do that. Draw something. Even if it's wrong, draw something. Oh, yeah. So guys, what might that something look like? Well, let's think about this. Let's start at the beginning. And our beginning is H2SO3. Will there be any H2SO3 in the beaker? Yes. In what instances will there not be any of whatever that is in the beaker? If it's strong, because that completely breaks apart. But if it ain't strong, you're going to have some of this. Not at the bottom. It's not a precipitate. It does dissolve, but it doesn't dissociate. All of it. But some of it does dissociate. And when it does dissociate, what will we now include in our beaker? Some hydrogen ion and some HSO3 minus. Without the minus, it's wrong. But is that the complete picture? No, because that HSO3 then goes on to break down as represented by the second equation. And when it does, what does it produce? It forms sulfite and what else? More high. But guys, watch this. Do this even though you would never do this on the test. Write another H plus, but make it smaller. And now I want to talk concept, and then I want to talk what you would do on the AP test. So guys, focus on the hydrogens. Where did this hydrogen come from? The first protonation. There's a fair amount of that. Where did this hydrogen come from? The second protonation. And there's not as much of that. So the question then becomes, and guys watch, when is there enough of this hydrogen that we need to include it in the total amount of hydrogen when we come up with pH? And that's the answer, 10 to the third. So if these are close enough to each other that they're less than a factor of 10 to the third apart, then this amount is large enough compared to that amount that we need to keep track of both. But guys, in this case, because they're different by a factor of 1,000,000, this number is so small compared to that number that trying to chase it down doesn't make sense. Does that make sense? Now, what would you put on the AP test? And the answer is this. Don't put both hydrogens. Because on the AP test, they will, and in a situation like this, they will ask you what species exist in solution. They won't ask you in this context how many. And so you're just representing type and not amount. Because the minute you represent amount, you're now starting to talk about stoichiometric relationships, and in equilibria, that's too hard to do. Did that sentence make sense? Okay. So they would just ask you for types and not amounts. So are we good right now on polyprotics? Yeah? All right, here we go, guys. It is now time, to talk about the interesting stuff today. It is time to talk about the pH of salt solutions. This is an interesting next step in our conversation. So guys, we got some water. Assuming this is distilled water, which you all know that it's not, what's its pH? Yes. We add some salt. And we do this. Now what's its pH? Actually, still 7. But, that's it. Guys, but not all salts will the answer be 7. So in order to understand this, we need to first of all talk about why is that still 7? And once we understand why that is 7, we can then talk about why other salts are not 7. But to do that, what do we need to understand? What happens when salt dissolves in water? Oh, yeah. What does this note say? Oh, you almost did that again. I had to beg you to write things down. But that doesn't get a mark, but this does. Okay, here we go. Have you guys ever thought about all the stupid stuff we do here that has nothing to do with chemistry? All right, here we go. And guys, you know that this is going somewhere. Oh.
When an ionic substance, such as sodium chloride...
Do you find that soothing? No. She just leans right into it. I love it. I love it.
...is placed in water, water molecules interact with the ions on the surface. If the salt is soluble, the attractive interactions with water molecules overcome the ionic attractions within the lattice. The solvated ions move off the surface and become separated in solution. Notice that water molecules...
That's where we stop. No, you haven't seen the end of this in a long time. Okay, guys, this is where we need to stop. Because right here, we have the answer to why is the pH of sodium chloride water 7. So let's talk. But we're going to be on this still for probably the next 10 minutes. So let's talk. So, guys, what are the forces of attraction right now that allow those water molecules to grab a hold of the ions and carry them into solution? They are intermolecular forces, but let's talk about which type. Ion dipole. Good for you. Okay. So, but guys, this is the thing that we've got to understand. And this is way back to the beginning of general chemistry. When salt dissolves in water, is that a physical or a chemical change? Hold on. When sodium chloride salt dissolves in water, is that a physical or a chemical change? It is a physical change, which means there is no breaking or forming of bonds. There are simply ion dipole, intermolecular forces that allow the water to carry the ions into solution. Good? Okay, so as a result, these water molecules are still intact and they're bonding, they haven't broken apart, and consequently the water hasn't changed and it's still pH 7. Does that make sense? Okay, now, what if this green guy was no longer chloride? What if this green guy was a substance, an ion, that could act as a base? Hold on. What if, and let's not say what if, we're going to go, what would it do? So let's say this differently. Chloride, green guy, is no longer chloride. It is now an ion that can act as a base towards water. What do bases do? Accept hydrogens. So now this is not an innocent little chloride happily IMFing off into the water. Guys, this is now a reactive base. This is now a substance that doesn't just interact with the water, it reacts with the water, and it functions as a base, and it rips off a hydrogen and takes the hydrogen away from the water, because that's what bases do. Does that change the pH of the water? Because now we're releasing hydroxides, and that will make the solution basic. Does that make sense? Now let's go over here. Guys, what if this is no longer innocent little sodium? What if this is an ion that has, I'm going to try to draw this in white. What if this is, no, I'm going to leave it. What if this is an ion that has the ability to grab a hold of an OH? Right? Because watch, the charge of this ion is positive, right? Positives and negatives attract. So what if this ion had the ability to grab a hold of this and pull it away? Will that change the pH? Yeah, because now we're releasing hydrogens into water, and that affects pH. So when we talk about the pH of salt water being NaCl, it has a pH of 7 because the salt dissolves into the water, but it doesn't react with the water. But other salts, that is not the case. Other salts, these ions don't just dissolve into the water, they react with the water. And if it's the negative ion that reacts with the water, it's going to grab a hold of a hydrogen and release hydroxide. Make sure that makes sense. Don't look away. This is important. Guys, if it's the negative ion that reacts with the water, it steals a positive hydrogen. That releases an OH, and what does the solution become? Basic. Now, if it's the positive ion that can react with the water, then the opposite happens, and the positive ion grabs an OH, and the hydrogen is released, and that makes the solution acidic. So what now is the question that we've got to answer to really understand this? which ones do that? Right? So let's do this. Do you understand why that in question is important? Hold on, wait. Do you understand the chemistry? Let's recap. Sodium chloride doesn't do this, and that's going to be important in a minute. Sodium chloride doesn't do this, but some salts do. If the negative ion is reactive towards water, it'll take in a hydrogen releasing OH and it's basic. If the positive ion is reactive towards water, it'll take in an OH releasing hydrogen and that's acidic. You good on the chemistry? Not yet. So now the question becomes, which ones do this? Well, guys, to answer that question, we need to have a conversation about salts. I think you should write this down with me. Do you understand where we're going right now? We're answering the question, which ones do this? But to answer that, and don't write until I tell you to answer that, the question that we're going to think about first is, why does table salt, when I say salt, do you know I mean NaCl? Why does table salt not do this? Well, guys, do this. Draw a yields arrow. Go ahead and do this. Right in the middle of your page. And then write NaCl over here. Okay, so here's what we're saying. We're saying sodium chloride, salt, table salt, does not mess around with water. The question is, and Matt, you were right on this. You said the important word, but I want you to wait on it for a second. How do we know? How do we know? How do we predict that sodium chloride doesn't mess with water? And guys, the answer is this. If you want, and hear this carefully, if you want to know if a salt messes around with water, you got to talk to its parents. You learned something a long time ago, and I know you've forgotten it. Because right now in your mind, you think that salts are ionically bonded substances. And that's true. But you actually learned some time ago, and you've forgotten that there's a better definition of a salt. A salt is the product, the ionic product of an acid-base reaction. Watch. So, here's what I'm proposing to you. To understand why sodium chloride doesn't mess around with water, you don't need to talk to sodium chloride. You got to talk to sodium chloride's mom and dad. So now we got to figure out who's mommy and who's daddy. So, who's mommy? Well, guys, mommy is HCl. Who's daddy? Daddy is sodium hydroxide. Yeah, how do you know? Here's what you do. You go to your salt and you take the positive ion and hook it up to hydroxide. And you take the negative ion and you hook it up to hydrogen. Think about why. All salts can be understood as the product of an acid-base reaction. Let's say that again. All salts can be understood as the product of an acid-base reaction. So you don't need to look at the salt, you need to look at the acid and the base that can make the salt. And so take the sodium, add OH, take the chlorine, add hydrogen. Now, let's talk about mom and dad. HCl, strong or weak acid? Strong acid. NaOH, strong or weak base? Strong base. Now, and Matt, this is where I want you to say the word. Listen, what do you know about the conjugate base of a strong acid? It is worthless, negligible. What do you know about the conjugate acid of a strong base? Negligible. So guys, this is a worthless acid. This is a worthless base. Consequently, it doesn't mess around with water. Can I say that again? So guys, this is the logic in reverse. Does sodium chloride dissolve in water or react with water? How do we know? We go and look at mom and dad. How do we know mom and dad? Well, we take the sodium and we add a OH. We add the negative, take the negative chloride, add a hydrogen. We go back to mom and dad and we go, hey mom, are you strong? Yeah, if you're strong, then your conjugate base is negligible. It's worthless. What does that mean that it's worthless? Well, it's a worthless conjugate base. And if it's a worthless conjugate base, it doesn't mess around with water. It can't take hydrogens from water because it's worthless. And then we go back to its conjugate acid and we go, hey dad, are you a strong base? Yeah, strong base. What do we know about strong bases? We know their conjugate acids are negligible or worthless. What does that mean? Well, that means this thing cannot act as an acid towards water. And because mom and dad are both strong, mom and dad's kids, the conjugate base combination, are worthless, and these don't react with the water. Does that make sense? You okay? Now guys, watch this. Let's do this. We're going to do a new salt. We're going to do sodium fluoride. So now let's look. This is now sodium. This is now fluorine. What will these do? Well, guys, to answer that question, let's go back over here and let's play a similar game. So now our salt is sodium fluoride. So we don't need to talk to sodium fluoride. We got to talk to mommy and daddy. So who is the acidic parent of sodium fluoride? Who is the acidic parent of sodium fluoride? HF. Who is the basic parent? NaOH. Now, guys, let's think about this. Can we join, or are you okay? Brandon, are you okay? Okay, and if you have questions, please stop and ask. You guys okay? Okay, so, guys, now let's think about this. Is HF a strong acid? No. Why not? Why is HF not a strong acid? Because fluorine is not worthless. Guys, don't write this down, but the thought is this. HF dissociates like this into H and F. But because fluorine is not worthless, it can grab the hydrogen and move backwards. That's what makes HF weak. As a result, we know that fluoride is an effective base. So this is not worthless. Let's leave it at that for now, but this is not worthless. How do we know? Because HF is a weak acid, and weak acids by definition have conjugate bases that function as bases. Now let's go the other way. Strong base? Yep, so what do we know about sodium? Worthless conjugate acid. So now let's take that idea and let's jump back here. So guys, what did we learn about sodium? Still worthless. So no chemistry happens there. But what did we learn about the fluoride ion? Not worthless. So now you got to figure out what's going to happen. So what will a negative fluoride hook up with? The positive hydrogen or the negative OH? Positive hydrogen. So this will literally steal a hydrogen off of water, releasing OH into solution and forming a basic solution. So if you put sodium fluoride in water, what's going to happen to the pH? It's going to go up because it becomes basic. Does that make sense? You okay? So now let's do this. let's reset the stage again, but now let's make our salt aluminum chloride. Now what's going to happen? Well, guys, in order to figure out what's going to happen, we got to figure out where aluminum chloride came from. Who's its daddy? Who's its mom? Well, so our acidic parent, and guys, we don't even have to balance these. Our acidic parent is HCl. What is our basic parent? Al, and we may as well write it correctly so long as we're at it, AlOH3. Okay, so what does this mean? Well, HCl is a strong acid, yes? So what do we now know about chloride? Worthless. Yeah, no, okay. However, but now, guys, what about aluminum hydroxide? Is aluminum hydroxide a strong base? It is not. Consequently, aluminum ion is an effective conjugate acid. So we take that idea and we transfer it over here. So now we've got chlorides and we've got aluminums, and aluminums plus 3. So does the chloride attack the water? No, it's a worthless conjugate base. Does the aluminum attack the water? It does, because it is actually an effective conjugate acid, and consequently, as the aluminum attacks the water, what's it going to pull from water? OH. So it's going to pull the OH from the water, hydrogen is given away, and the pH of the solution goes down. It becomes acidic. You get the idea? Does that make sense? So now, guys, what about this? What if your salt is aluminum fluoride? Right. Which very politically correct of you, Matt. Write this down with me. One molar CO, ClO4, 2. 0.1 molar. 0.1 molar rubidium cyanide. 0.1 molar strontium nitrate. 0.1 molar potassium acetate. This was actually off the free response section of an AP test from 7 or 8 years ago. Interestingly, is they expected you to be able to solve this in under 3 minutes. No, you don't know the question yet. Close. You guys got it? The question said this: put these in order of increasing pH. Put these in order of increasing pH. So, how do we do this? Well, guys, what we need to do is we got to do all of this lineage stuff. Right? Yeah, that's right. We need to think about parents. But guys, we've got to do this efficiently. So let's get efficient about this. So as we look at this, all we've got, and you understand these are all for salts. So we look at this and we go, we've got CO and we've got ClO4. What we need to do is, and do this with me, we need to ask ourselves, who are their parents? So guys, who is the basic parent of this salt? Well, it's cobalt hydroxide. Did that make sense? I'm going to write it down, but I hope you don't need to. That's the basic parent. Is that a strong base? No. So what does that tell you about the conjugate acid? It's not worthless. Move on. What is the acidic parent of this? HClO4. Strong acid? Yes. Worthless. Cross it out. What you're trying to do here, guys, is find the worthless children. I'm probably going to get in trouble for that at some point. But, so let's go here. What is the basic parent of rubidium cyanide? RBOH. Is that a strong base? Well, guys, oh boy. Group 1 and heavy group 2 hydroxides. Gone. It gone. Understand it's in solution, right? But it's not doing chemistry. So now who is the acidic parent? HCN. Strong acid? Leave it alone. Now guys, moving to our next salt, strontium nitrate. Strontium, strong base, strontium hydroxide? Yeah, group 1 and heavy group 2. This is part of the reason why I had you memorize the strong acids and bases over the summer. Remember, it's group 1 and heavy group 2. So that means this is a negligible acid. What about NO3? Strong acid parent?
Yes.
HNO3, strong acid, gone. What is the pH of this solution? Write it down. That's like table salt water. Now, let's look at this one. This is acetate. If you can't see it, it breaks here. So what then is potassium? Strong base, KOH, right? Strong. Where'd it go? There, strong. Get rid of it. But now, guys, C2H3O2 is CH3COO. It's acetate. Is acetic acid a strong acid? It's weak, and therefore it's not worthless. Okay, so guys, now what we've done is we've excluded all of the ions that don't do chemistry. At this point, I'm going to write down, frankly, more than maybe some of you need to. How you handle this is up to you. But what we've done now is this. We know that cobalt's going to do some chemistry with water. We know that cyanide is going to do some chemistry with water. And we know that acetate, this has nothing to do with charge. We know that acetate is going to do some chemistry with water. We got to figure out what chemistry. So if you want to write this down, you're welcome to. If you don't need to, you're fine, but let's talk. So guys, cobalt ion, what will it do to water? Will it attract an H or an OH? OH. So this is going to form COOH2 and hydrogen ion. Now let's look at our next one. I'm going to put this in silos. So guys, what about cyanide ion? What will it do to water? It'll take an H, and it'll form HCN, and it's going to release OHs. We've already established that this salt does nothing, the third one. Well, what about acetic acid, acetate ion? What will it do to water? Oh, whoa, because these are equilibrium. Sorry. It'll take what? An H. So it'll do this. Okay. So now let's look. So in this first salt, we've got hydrogen ion being released. In this second salt solution, we've got OH being released. In the third salt solution, we've got neither. And then in this one, we've got, not now, we've got OH being released. Or did I make a mistake? Oh gosh. Thank you. Okay. So, we can do this. Well, we can at least, we're putting them in order of increasing pH, right? What is the pH of this going to be? Lower. So this is going to be number 1 because it's below 7. That's the lowest pH. Then, guys, this is going to be number 2 because it is 7. But now we've got a problem. And the problem that we've got is this. Both of these are releasing OH. Which one is going to release more? In order to know, what do we need to know? We need to know the dissociation constants for acetate ion and cyanide ion. And the base that is a better base, as represented by Kb, the base that is a better base will do a better job of ripping water apart, making more OH and having a higher pH. Does that thought make sense? This is where this gets evil. They didn't give you the Kb's, they gave you the Ka's of the parent acids.
Well, it's just the weaker one.
Yeah, so right. So guys, that's the thought. Right. So guys, they didn't give us the Kb for acetic, and this is back, Daniel, to your question about acid conjugate base. They gave us the Ka for acetic acid, and they gave us the Ka for HCN. So guys, think about this. If these are the Kas for the parent acids, the Kb's will be the inverses relative to 10 to the negative 14th. So which one is a stronger acid? The acetic acid or the HCN? The acetic acid is a stronger acid. Therefore, its conjugate base will be weaker. And the HCN, which is a weaker acid, will have a stronger conjugate base. Does that make sense? So let's take that thought, hold on, let's take that thought and come back here. So guys, CN is a stronger conjugate base, as established previously. So if CN is a stronger conjugate base, this will give off way more hydroxide than this one will. So this one will have the highest pH. This will be 4, and then relatively that one will be 3. Does that make sense? So guys, and I love that we have this wiggle room. I would encourage you, if you understood everything that we just covered, throw this away. If you didn't, this is actually a representation of this parenting thing. But if you understood what we just did, please don't reference it because it might confuse you. How are you going to know? You're going to do this homework. And it really is that short. No, I know you don't trust me.